All right, I want to thank everyone for joining us today. My name is Andrew Sartorelli. I'm a technical support specialist here at Autodesk. Work out of our Munich office doing support for simulation mechanical, Nastran In-CAD. And today I've got Bart McPheeters from the sales organization joining us. Bart's got over 30 years experience with Nastran and doing dynamic analyses. Today we're going to be talking about getting to the fundamentals of the modal analysis, hopefully answering some of your questions about when to do a modal analysis, how to do a modal analysis, what's going on in the background. So as always, we have our slide deck available for download after the presentation at the box folder with the link at the bottom of your screen there. So what are these Help webinar series? It's our monthly technical discussion. So we'll go over topics submitted by attendees like yourselves in the post-webinar surveys. So we kind of pull information from that to come up with our topics for the following couple months, usually 20 to 40 minutes, and we leave some good room there for Q&A. So if you've got questions about what we're covering today, maybe some other questions related to Nastran In-CAD, certainly feel free to ask us about those. Most recently, we did a webinar about what's new in Nastran In-CAD Subscription Advantage Pack with the product manager, Mitch Muncy. That was in October, so if you haven't had a chance to take a look at that yet, definitely recommend going to our YouTube channel and going and reviewing that. It's got some good information about what great new enhancements we've got in the latest version. Coming up next month, we'll be going over performing weldment analysis with Vince Adams, also part of the sales organization, and Dean Rose, who's a technical support specialist handling Nastran and our Helios products. As always, we post these on the SimHub. We also may have direct emails going out to you, and once the webinar is done, we'll go ahead and post that to our YouTube channel, Autodesk Sim 360. I think at this point we're going to pause for a second, and we're going to throw out a couple poll questions for everyone to answer for us.
Okay, let's see what we've got. Let's pick a poll here. Where'd they go? There they are. Here's a poll question for you. Up is, have you ever performed a dynamic analysis? Is everybody seeing these? I probably have to say launch. There we are. Okay. Give everybody a couple minutes to answer this. Performed a dynamic analysis, and this would be modal analysis, time-dependent frequency response, anything like that. Okay. Looks like some have, some haven't. Okay. We got everybody here.
So let's go ahead and share those results, Bart, and let's see what everyone voted here.
Okay. How do I share these there? Let's close the poll here. And here's our results. Share. Here we are. Looks like most people have not. A couple people have, so that's a good thing. So, hopefully this will be a useful webinar for people then. Let's go on to a second poll. Talk about what kind of dynamics do you encounter. And there's any number of types of dynamics here. Vibration, shock, impact, drop testing, large motion dynamics. See if anybody's come across any of these or has any, not necessarily analytically, but have the parts or products you make ever come across any of these problems.
Wow, looks like a lot of responses coming in here.
Yes, they are.
The pack seems to be impact and drop testing.
Yes, it does. It's always nice to know some dynamics and modal characteristics before we do impact and drop testing, so that's a good one. So here, let's, what do we got? Looks like half our people, looks like more people are jumping on right now. So let's give just another minute here. See if we get any more votes. Okay. Let's close out our poll here. we'll take a look at our results here. Impact and drop testing, leading by a large margin. Large motion dynamics, too. We'll talk a little bit about that at some point. We may have some questions about that. And then vibration, shock, other types of analysis. Okay, good enough.
And that brings up a good point. If you have questions at any point during this presentation, feel free to use the question sidebar, and we'll try to bring those up towards the end of the discussion when we've got some time slated for that. So we'll continue on with our presentation here. So what's in the news for Nastran In-CAD? We've got the Subscription Advantage Pack coming out in September. So that's available only to customers on subscription. You'll see that in your Autodesk account under Product Enhancements. Definitely a lot of great features there, from mid-surfacing to bearing loads. So definitely take a look at that if you haven't already. We did some great work to the user interface there and made some improvements. In the older news, we've got self-paced training that was published on the help page, some essential skills videos, and an update too for Inventor.
And if you haven't already made your plans, Autodesk University is December.
So at this point, I'm going to turn it over to Bart, who's going to share some of his expertise with dynamics and talking about natural frequencies and modal analysis.
Okay, I guess when I talk about modal analysis and natural frequencies, the first thing is what exactly is a natural frequency? And every item, whether it's big or small, has one or more frequencies at which it will vibrate. Sometimes things like rocks vibrate at really, really high frequencies, but a classic case of a natural frequency is a tuning fork. It's built and constructed so that when it vibrates at a particular frequency, whether it's A or F or G or whatever your tuning fork is. So that's what a natural frequency is. I'll move to the next slide here. Actually, things have many different frequencies, and any particular part or item is likely to have lots and lots of different frequencies. If you ever hit the tuning fork in the wrong place, you've noticed instead of getting a nice clear single tone, you'll get a funny mixture of higher frequencies and lower frequencies, and it doesn't sound like that nice tuning fork. And that's just because when you hit it in this other place, you get a different frequency. So that's just demonstrating there's multiple frequencies that items have. In fact, they probably have an infinite number of frequencies. And when you actually do hit something, you're creating a vibration, and each vibration has a particular shape. So if you hit your tuning fork correctly, you get the fundamental tuning fork mode shown there on the left. And this will end up with almost a pure note, which is why you can use a tuning fork to do that. If you mishit your tuning fork, you'll end up with the clang mode that we show on the right there. And when you're doing that, you're getting a little bit of vibration at the primary frequency, but you're getting other vibrations at a different frequency. So each natural frequency that you have of a structure is associated with a particular shape of vibration, and that's what we'll call the mode shape or the eigenvector.
Bart, I've got a question about this. I've done a couple, modal analyses myself. I haven't seen displacements kind of associated when I take a look at my mode shapes. What does that value mean?
It means it's the shape. It really means nothing magnitude-wise. Natural frequencies are arbitrarily scaled. Back in the day when you got printed output, we did what was called a max normalization. We found the largest displacement, divided everything by that, so you could look around and find a 1. Nowadays we use a different normalization, but it's still arbitrary. The magnitudes are arbitrary, so if you calculate stresses for a mode shape, they will be arbitrary stresses. And so we tend to discourage people not to look at the stresses from a mode shape because they don't really mean anything. The magnitude is arbitrary. So, why do we actually care about node shapes and natural vibrations? Well, obviously, no presentations on vibration and resonance would be allowed unless we had at least one picture of the Tacoma Narrows Bridge. And the reason we do that is things can be put in places where they're subject to vibration. You can have a part that's in a vibrating environment. It's on a car. It's on an airplane. It's being shaken somehow. And if you have a part and you shake it at its natural frequency, it'll experience resonance. So each cycle, the magnitude will increase just a little bit, and over time, that magnitude will get larger and larger and larger, and the part can shake itself apart, just like the bridge did. You had a wind loading on the bridge that was in tune with a resonance, and it caused the bridge to rock a little at the bridge's natural frequency, and it rocked a little harder and a little harder and a little harder, and eventually shook itself to pieces. So that's why vibration and why we care about it. So what can I do about that? Well, obviously we're here because you can actually calculate a natural frequency. You don't actually have to build something and test it. You can do a modal analysis or a natural frequency analysis, and in a finite element code such as Nastran In-CAD or Nastran, and come up with those natural frequencies so you can do it. And I thought before we go into actually how to do it in In-CAD, I thought I'd do sort of a quick review of dynamics and what it actually means to calculate a natural frequency. So we'll start off. In a static problem, linear static problems, you apply a force to the model, up here, big red arrow, and the force acts against some kind of spring or stiffness and causes a deflection. In the equation term, that's F equals KU or F equals KX, where the terms are as defined. And that's basically the sum total of a static problem. If you have lots of springs or a finite element problem, you can express it in matrix terms, where you have a whole column of forces applied to the individual places. You have a whole bunch of deflections at the different points, and then you have a stiffness term that relates the forces to the deflections. So that's statics. Now dynamics, on the other hand, introduces another term. Dynamics brings in Newton's law of motion. If we're simply looking at something free in space, like this rocket here, you apply a force to the rocket, and the rocket will accelerate proportional to the mass. Newton's law of motion, F equals ma. Similarly, if you have lots of masses in your model, you can express it as a column vector. Oh, I have my brackets backwards. A column vector of forces, a mass matrix, and a column vector of accelerations, so that we have those. In finite element terms, however, we have mass, we have stiffness, we have all of these. So what you do is you combine them together. So now our force is a combination of the mass times acceleration from Newton's law and the stiffness effect based on the deflections. So we have a static force and we have an inertial force on our object that go into calculating the response of our object and the deformations. Accelerations, the second derivative of displacements. So you can say that's the mass times d squared u dt squared, second derivative, times k. So now we really only have one variable, which is the displacement. It's a differential equation. And this is sort of a basic, really basic equation of motion. Force is a function of those two. Now, in general, it's a little bit more complicated because the deflections can vary in time, the forces can vary in time, and in terms, we often use P instead of F, and we're using X instead of U, but it's the same idea, it's the same equation. And there's another term in here called damping, and the damping on a finite element model is proportional to the velocity. So I have a displacement, I have the first derivative that's the velocity, and the second derivative that's the acceleration. So that is a general equation of motion. Now we're talking about free vibration, and that's what our natural frequency are. So in the free vibration, we don't have any loads, so P or the F term is 0. We're going to ignore damping for the moment, just because damping adds a complication to it that sometimes is important, sometimes it's not. And So we end up with a much more general solution to the equation of motion where we have the mass term, stiffness term equals 0. And in the fine way of differential equations everywhere, we're going to assume a solution. We're going to say my solution is a sine wave, so it's varying positive, negative, and it's vibrating. Okay, that makes a lot of sense. We do a whole bunch of substitutions into that equation, and lo and behold, we come up with the classic form of the equation. And the classic form here is sort of what you see up here. You have a determinant, a mass, you have this lambda term, and you have this phi term on the end. And this is what's called a classic eigenvalue problem. When you solve for natural frequencies of a model, you're solving an eigenvalue problem. Buckling is actually an eigenvalue problem too, and it uses the same solver. But normal modes are this. And so what you can see is in a normal mode, you have a situation where the stiffness here is roughly balanced by the mass. So you have a situation where this determinant is equal to 0, where the two terms balance. And you end up, for every degree of freedom in your model, or every node in your model, you'll end up with a point where the mass and the stiffness balance with a little factor here, lambda. And that little lambda here is actually the natural frequency. The natural frequency is actually the square root of lambda, but the same idea. And for each one of those, you have an eigenvector. And the eigenvector here, the phi term on the end, are the mode shapes. So when I actually solve this equation for these points where the determinant is equal to 0, I end up with a lambda and a phi, and a lambda and a phi, and a lambda and a phi, one of those for every term in my matrix. And that is the basics of natural frequency analysis.
Awesome, thank you, Bart. So I think at this point we'll jump in and start doing some in-CAD here. So I've got this basic propeller model. For those of you that have run through some of the online tutorials that we're talking about earlier, you may be a little bit familiar with this. So we'll go into the in-CAD environment. And so by default, it's going to set it up as a linear static analysis. We can edit this, and we can just change this over to a normal modes. We'll click OK, and it's going to change some of the settings for us there by default. So we'll go in, we're going to edit our physical property. It's got a generic material, but I'm going to go ahead and change this, and I'm going to select from our library here that I want a alloy steel. I'm going to click OK. It's going to pre-populate all these fields for me, which is pretty handy. So we'll click OK. And now we're ready to simply mesh our model. So we'll refresh there, and that should mesh.
Are we going to hold this one on the shaft, or are we letting this one go crazy?
So we'll fix this one first, just to show some of the fundamentals here of modal analysis. We'll add in a constraint, and we're just going to fix it. So we'll fix it right there with a shaft would kind of attach. We'll click OK. We'll take a look at our modal setup here. We'll look for at least 10 modes. We can leave everything else at the default here, and we'll give this a run, and we should be okay.
What it's going to do is it's going to find the first 10 natural frequencies of this little propeller deal when we're holding it on the shaft like that. So it's very easy to do. The loads were 0, so we don't have to put any loads. And actually, if you put loads in, Nastran will just ignore them on a natural frequency analysis.
So we can see the eigenvalues Bart was talking about earlier. We can see those being generated in the output. And we'll give it another couple seconds here, and it should give us our results. We can see it's writing out the results file now.
And we took all the defaults, so it provides stresses. But remember, the eigenvectors are arbitrarily scaled, so the stresses don't really mean anything.
So we can look at a contour plot here. And what I'll do, I'm just going to change this over. By default, I went to stress. As we talked about, the stress doesn't matter, so we'll go to displacement. And now we can take a look at the shape here.
Mode 1, 670 hertz. So these are representing the first 10 natural frequencies of the model. And you can see we've got 3 blades. They sort of come in triplets because we got 3 blades. So we got 3 modes that are about the same. And then we've got some other modes that are a little different. Some twisting modes where the blades are twisting. We had a couple modes where the blades were bending back and forth.
So one question I get a lot on support is kind of how do I know, that I've captured enough information with my modal analysis? One, the initial screen, you get the option to, choose the number of modes, and the question comes up, how many should I enter there? There's actually a really easy way to figure out based on the output file of the Nastran analysis if you need to go in and make a change to this. So what I'll do, I'm just going to pull up the folder I have for this, and we'll look at our out file. So this gives us a whole bunch of information from the analysis. Some of it pertinent, some of it not pertinent. So we're going to scroll down, and I know there's a section here called modal effective mass.
I think if you search for the word cycles, you get this little table there.
Ah.
Little Nastran trick from over the years. Yeah, here's this little table. It's called percent modal effective mass. And in any particular model that you have, you will have, any model has 100% modal mass. And so you look at this percent effective modal mass table, and it tells you how much of that modal mass each mode actually contributes towards that 100%. And so you can look at this and you can see that, and this is in each direction. If you think about a cantilever beam, if I shake a cantilever beam up and down, it's going to vibrate up and down, and so that up and down mode will actually have fairly high modal mass in that direction. If I shake the cantilever beam sideways, though, the beam's going to move sideways, so the up and down mode will have low modal mass in the sideways direction, but the sideways mode will now have modal mass. So if you look at this, we've got a lot of mass in the T1 direction, which is along the propeller shaft. Actually, we don't have a lot. We have 18%, which isn't a whole lot, but it's in the T1 direction because that's the direction the blades are moving. We got a little rotational mass in R3 too.
So one rule of thumb that kind of I like to use is I like to make sure I've got at least 85% modal effective mass in the degrees of freedom that I'm really interested in to make sure I'm going to be capturing the dynamics fully. So you can see here with T2, which corresponds to the Y degree or translation in the Y, we don't really have that much modal effective mass here. So if we really need to amp up the number of modes that we're calculating to make sure that we capture the range where we get the dynamics for this degree of freedom. So we can go back. What we can do is we can simply increase the number of modes here. So I could amp it up to something like 20, 30, and rerun the analysis, and then go back to that same output file and check to see that I've got a modal effective mass cumulative over 85%.
Yeah, sometimes you'll struggle to get that because this propeller, most of the mass of this propeller is sitting in a big lump, and that lump is attached to the shaft. So it's going to be really hard to get the dynamic behavior of that big lump of steel. It's probably a fairly high frequency piece of steel, so it's going to be hard to get that modal mass, but it may reach a point where it's beyond the frequency that you care about.
So this brings up a couple points. When you're running a modal analysis, you need to have a material that has mass associated with it. Otherwise, if we go back to this equation, then we have a 0 there, and everything kind of cancels out. And we need stiffness as well. Otherwise,
yeah, k minus 0 is going to equal 0 no matter what the k is, so you end up with an indefinite solution. And by the same token, as Andrew was just saying, if m is 0, you have k minus 0, and that's going to be 0 no matter what k is. So both of those are required in order to do a modal analysis. So make sure you have densities or masses in your model.
And thankfully, Nastran will actually give you some warning messages and error messages if you do that. So if I go in here and I say, all right, my density is now 0, I'm going to enter that. Maybe you've made a mistake. You meant to enter something else. You left numlock off, and you don't have an actual value in there. So we'll get this, and we should get a fatal error message here pretty quickly.
Come up and say your model has no mass, or it'll say, what is it? The mass matrix could not be. There it is. Non-zero global mass matrix is required. That's telling you have no mass. And without any mass, natural frequencies make no sense.
So one really nice thing that we've updated recently is all of these error messages now link to the Nastran help. So you can pull up information on these error messages. So not everyone was kind of aware before that if you moused over an error message and pressed F1, it would pull up some information in the Nastran help on that. Now we can just click this, and it brings us directly to the article on this, so we can see what we need to do to fix this. We need to specify a material density in our property card. So we can go back. We'll just go back, and we can make the correction here now. We'll just select the material again from the library, click OK, and it's back again populated with a density. So, what happens if some of these are 0, or, like we said, you're going to cancel terms out. But one really great feature of a modal analysis, and I know Bart, you use this a lot, I use it a lot, everyone else on tech support uses this a lot. We can debug static analyses to figure out where a problem may lie. If we're getting a non-positive definite or a 0 in the diagonal of the stiffness matrix, we can use a modal analysis to then troubleshoot this static model and hopefully allow us to quickly resolve the problem. So I'll show a quick demo of that right now. We jump back into.
Yeah, there's nothing worse than that non-positive definite, because generally that error means something's not attached and something's flying away, and sometimes you have no idea where it is and you don't know how to find it. So what you can do is, first thing I always do is change it from a linear static to a modal analysis, which is sort of what we're doing here. We're going to get rid of
what we'll say is maybe we want to allow this to translate, but we don't want it to rotate. And I'm going to go in and I'm going to add in a force here, and I'm going to say it's being pushed. We look at our coordinate system in the x direction. Maybe it's 10,000 newtons in that direction. And let's go ahead and we'll add a pressure on these surfaces here. So we'll go up to loads here, select the pressure. We'll just go select all these surfaces, and we'll say this is 10 MPa.
If we're really good, we know that the pressure balances the force, so that we have a nice balanced situation.
Right.
But even so, even if we have the forces all balancing, when we try to run a static analysis on this,
so go ahead.
Here we are.
Give this a run.
And it's always fun. Sometimes you get an error that says non-positive definite matrix detected, stiffness detected. Sometimes it'll tell you you have a singular degree of freedom. Sometimes it'll tell you it's unable to do something. But singularity detected component 3 tells me that no stiffness in component 3, and it's probably the whole model. And when we look back and we think about it, that, yeah, we put pressures putting one way, forces pushing another way, but there's nothing keeping the model from moving in the other direction. So it makes sense, but this is a point where I've just run this and I've gotten this singularity. What the heck is it? Let's really quickly change it to a normal modes analysis. Do a really quick, all you had to do was right there. That's all Andrew did. Change it from static to normal modes and run. That's really all you got to do. It's a very, very easy way to debug things.
Right, and it's, on this model, it's a single part. It's really easy to understand the obvious mistake I made setting up my constraints. But if you've got a more complex model, sometimes it's not so easy to understand where a problem may lie. And that's where this doing a normal modes analysis is really a great troubleshooting step there.
Yeah, often I'll have a model comprised of several parts, and I'm using glued contact or bonded contact to hold them all together. And I run my analysis and I get the singular part or the non-positive definite error, and I don't know what it means. So I go back, I run my modal analysis, and lo and behold, this is what I get, a zero frequency. And I look at the mode shape of the zero frequency, and the mode shape of the zero frequency tells me it's all moving in some direction here.
So we can cycle through our translations here, and we can see that the entire part is essentially moving. It's amplified here 32 millimeters, so we know that's not a real displacement, but the entire part is moving, as we can see here. And if we were to look at Ty, it's going to be 0. So we know this is a rigid body motion for our x degree of freedom in the translation. And then we cycle to our second mode here. We see this is with translation in the y. So if we switch to Tx, as our result vector here, we get 0. So everything in this mode is moving in the Ty direction. And we can again cycle through, and we see that again for the other modes. So if you see a frequency coming out of your modal analysis that's 0 or approximately 0, to me that's a trigger that you've got rigid body motion. And when you're doing this troubleshooting, that then tells you where you're missing constraints.
When I often find that with my models held together with the bonded contact, invariably I plot my little displacements and I find one part that wasn't attached. And either my activation distance wasn't large enough to catch it and the contact didn't stick it, or more normally I put in separation contact or something. I put in the wrong kind of contact or just forgot the contact. And so I've got a part that's flying loose, and the mode shape is 0 frequency. You plot the shape of it and you see that part flying around. Again, very easy to debug parts that are not attached. Very nice.
So, why do we care about all this? Bart, what's the end result here? What do we get out of this?
Well, we get an understanding of the model dynamics, what natural frequencies it vibrates at, and what those natural frequencies look like. Sometimes you answer a problem like, is my problem really dynamic? And what we're finding with the propeller there was that the blades all have frequencies in the 300 to 2,000 hertz blade frequencies, but the hub isn't vibrating. The hub isn't necessarily dynamic unless we're thinking really high frequency parts. The other thing you can do, are my results in a ballpark? You can do hand calculations. There's an awesome book by a guy named Blevins called For Natural Frequency and Mode Shape. And you can look up in that book something that looks sort of like your part and do a hand calculation. It'll tell you what the natural frequency is in the mode shape. You can then look at your model and look at what you calculated and say, am I in the ballpark? Dynamics is a great way to check a static model because it tells you whether the mass is right and the mass distribution is right. And finally, more advanced dynamics problems, you need to know a lot of things in order to run those. Well, not a lot, but you need to know more than you need to know for modes. And for instance, I'm running a transient, a time-dependent analysis. How long does my time have to extend so that I get full cycles? Well, I don't know how long that's going to be unless I know how long a full cycle is. So I run a modal analysis. It tells me it's 30 hertz. I take the reciprocal of that, and I know how many seconds I need to run to get a single cycle. Similarly, I'm running an enforced vibration or a harmonic vibration problem. How far should I run it? Should I run it from 0 to 100, 0 to 1,000, 0 to 2,000? What frequency range is important? Well, if I've run my modal analysis, I can make a pretty good stab at it. I can say, this range is important.
So we've got 5 different kind of more advanced dynamic analysis types that I think a modal analysis kind of leads you into doing. So we talked about, when you do a modal analysis, the displacements and stresses you get out are kind of scaled. They're not actual displacements. So you're going to do something like a modal frequency response or direct frequency response to get that kind of information. When you want to get stresses out, when you know what your input frequency is going to be like, you can do these kinds of analyses and then get out actual stresses, actual displacements. So we've got those all available, those 5 in Nastran In-CAD. So I go up here and I just go to Edit. We can pull up some of these more advanced ones. Direct transient response, modal transient response, direct frequency response, modal frequency response, random response. And some of these, they're going to do the modal analysis for you. So the modal transient response and modal frequency response. Select one of these. It's going to have us set up a modal analysis automatically when we do that analysis type. But for some of the other ones, the direct ones, that's when it really comes into play, where you can do the normal modes beforehand, and then you have a good idea of how you really should set up the analysis. So if I take a look here and just do a direct transient response, and now we just get the dynamics set up. How long should we run this for? And that kind of information you can pull out of the normal modes and modal analysis.
It's even important for a impact analysis, because impact analyses are technically transient analyses. And when you drop something and it hits the ground or runs into something, it's going to start vibrating. And it's going to vibrate at one of the principal modes. And if you know what frequency that mode is, you know a lot more going in. So if you run the transient analysis and you see the transient runs, vibrates at 6 hertz, but you ran your modal analysis and it was 30 hertz, you may have a problem somewhere, or you may be exciting a different mode, or it gives you a lot of insight into what you need, even for impact analyses, because like the tuning fork, if you drop a tuning fork, it rings if it hits right. So if you know what that frequency is, you know what you're looking for in an impact analysis. It should ring.
So I think at this point we'll open it up for questions. So let's take a look here, Bart, and see if we've got any questions coming in from the audience. Doesn't look like we have any questions asked right now. So if you have something on your mind, not necessarily related to doing a normal modes analysis, modal analysis, if you've got a question about Nastran In-CAD in general, or maybe one of our other simulation products, feel free to ask it right now, and we'll try to tackle that.
I'll expand on that little impact analysis again. When we use In-CAD has an automatic impact analysis set up where you tell it where it's dropping and how fast it's dropping and what it's hitting, and it's a very simple setup. And we do all the time step setup automatically for you. But the way we do that is we're running a modal analysis before we run the drop test. And we run the modal analysis, it tells us what the natural frequencies are, and then we know how long we should be running the transient, how long it should take to get set up. So when you see the time steps that are automatically chosen, they're based on those natural frequencies. So yet another place for natural frequencies to be important. I see a question here.
It's like Eric asked here, do you have to run a normal modes analysis before a frequency or random response analysis?
The answer to that is no. You don't have to. It's just, well, you have, if you're running a modal frequency response, Nastran will run it for you. If you're running a modal transient, Nastran will run it for you. But if you run a direct frequency response or a direct transient, it's not necessary to run the normal modes analysis. You can do it and run it blindly. I find that I like to run the normal modes just because it's a check on the model, and it gives me a good feel that the results are going to make sense, so that I know what I'm going to get. But it's certainly not required unless you're doing one of the modal solutions.
So we can see here, just looking at a direct frequency response, we don't get that modal setup. If we go back to a random response here, we've got the modal setup option. So we know, it's doing everything all in once. So if you're familiar with simulation mechanical, you've got to do the modal analysis and then you do the random. This way, everything's all in one analysis.
And it helps you a lot because it sets it up automatically for you and starts it off, gives you a better feel for it.
So it doesn't look like we've got any more questions coming in here, so we'll go with one poll question here I think we've got left. Bart, if you want to kick that off.
Okay, I do have another question here. It says a direct frequency analysis requires a load of some sort, and why is that required? And the answer is a direct frequency or a modal frequency analysis, what you're doing is you're actually shaking something at a particular frequency, and this is where the modal analysis, in a regular normal modes analysis, you're finding what frequency and what it would look like if it were vibrating freely. When we do a frequency analysis or a direct or a modal frequency analysis, we're actually using a physical magnitude, and that's why you need a load of some sort, because the load actually tells Nastran how hard I'm shaking it and how much I'm shaking it. And the bonus is the stresses that you get out of a direct frequency response analysis are real stresses. So they're not arbitrarily scaled because we're putting in a real load, and the real load is sort of a scale factor on that. It's also nice not to put it in at the, if you put in your excitation at resonance, you'll get a very large response. Okay.
So let's kick off that last poll question there. I think we've got Bart.
Yes, we've got that last one. Let's pick it here and launch poll question. We're asking this one, just more of a reminder. We've done a lot of items that Mitch mentioned in the previous webinar, and we've done a lot of things with memory management and speed improvements in this release. So if you haven't done the SAP release, it's well worth doing. It's well worth getting and downloading.
Yes, strongly recommend it. Some of you may have noticed if you're using the initial launch version of Nastran In-CAD, my ribbon's a little bit different than yours. We've tried to make the ribbon a little bit more user friendly. We've added some more things you can do up there. So you may have seen the find thin bodies or the mid surface and offset. So we got some great things there to go in and do some simplifications to your model if you're working with thin parts to go in and easily surface mesh things rather than working with your full 3D solid bodies. So if you haven't done so, like Bart said, definitely go on and download that. We did get a question here. Great question. Where can we download the subscription advantage pack? So you can download it through Autodesk account, and there'll be a link on the left-hand side for product enhancements. Your account needs to have a Nastran In-CAD entitlement associated with it so that you can download the subscription advantage pack. So it's Part of that subscription advantage is, customers on subscription with Nastran In-CAD get access to it. So those customers that don't have access to it or aren't on subscription won't have access to this. So this is an additional benefit to be on subscription. So it's just important to make sure you've got your Autodesk account correctly synced up. And I think with that, we'll go ahead and close the poll here, and we'll share the results.
Okay, there we are. Yeah. Go download that. Download that release. It's definitely worth doing.
Strongly recommend it. So I want to thank everyone for joining us today. Bart, thank you for helping me out with this webinar. We'll be having another one next month on weld analysis and Nastran In-CAD, and we hope to see you all then. Thanks a lot. Take care.